this video, we will do yet another reaction of alkenes. This one is called Diol Formation. Please read section 6.5a, pages 232 to 233. It's a pretty quick read. And this is not a complicated reaction. It's another one that's a two-reaction, one-pot synthesis. So first you add osmium tetroxide, let the reaction occur, and then you add some sodium bisulfite and water, and you get a dipole, two OH groups adding onto the two carbons of the double bond. So this one is a little simple in that you don't have to worry about which carbon gets which thing because you're adding the same thing to both carbons. You do have to worry about the fact that it's stereospecific, it's syn, so the two things that you're adding on add to the same face of the alkene. So we come in like this, or like this. So let's talk about the first reaction. It uses an interesting reagent using an element that you probably have never heard of before, and it's a very rarely used element, osmium. It's also a very expensive and toxic element, but it does the job very nicely. So chemists use this reaction to do this particular job. So what does it do? Well, the osmium tetroxide forms this very interesting looking 5-membered ring in which 2 of the 4 oxygens attach directly to the 2 carbons of the double bond. It, of course, becomes a single bond in the process, and, of course, the osmium with the other 2 oxygens is still there. So if you look at the Lewis dot structure for this, the osmium actually is neutral, so there's no charge in this complex. But the important thing is that both bonds form at the same time, so there's no chance of rotation around this bond, and that's what gives it a syn stereospecificity. The second reaction is more complicated in terms of the mechanism. We won't talk about the mechanism at all, but it uses a reducing agent, sodium bisulfite, and water. And you might wonder, well, what happens to the sulfur? What happens to the sodium? What happens to the oxygens of the water? And that's all fairly complicated, and we're not going to worry about it. Notice it just says various reduced osmium compounds as a product. That's a bit of a problem because those need to be disposed of in some way, shape, or form, but we're not going to worry about that. We're just going to write the product. So essentially, the 5-membered ring osmium compound gets reduced, and hydrogens from the water actually end up attaching onto these 2 oxygens, and you end up with the 2 OHs. And notice that these 2 carbon-oxygen bonds remain intact. So they were put on in a syn fashion to begin with. They remain syn to each other after this second reaction. Now, it turns out there's an alternative method for doing this, and people came up with it because osmium is a very expensive metal, and so osmium tetroxide, as you might guess, is a very expensive reagent to use. And so what they discovered is if you use as your reagent hydrogen peroxide, you can put osmium tetroxide in as a catalyst, which means you can use only a very small amount of it, and it still does the same reaction, but it gets recycled so that those various osmium products that I mentioned earlier get turned back into osmium tetroxide by the hydrogen peroxide, and then it can do the reaction again. So essentially the hydrogen peroxide is recycling the osmium tetroxide, and so you only need a small amount of it. It almost looks like the H2O2 is the reagent that's adding across the double bond, but it's not. It's actually the osmium tetroxide that's doing that. So you go ahead and see if you can draw the products for this reaction. And I'm going to go to the next slide. There we go. So we're going to add the 2 OH groups across the double bond here. It obviously becomes a single bond, and we end up with 2 OH groups there. Same thing here. We're going to add 2 OH groups across that double bond. Now notice that I've drawn them. It looks like they're anti to each other, and I've mentioned that this is a syn addition. These look like they're syn, like they're supposed to be. These look like they're anti. In fact, both of them are just drawn in whatever the most convenient way is, because we really can't tell what the stereospecificity of the reaction is, these 2 products, and so therefore we just draw them in whatever is the most convenient way. But if you look at this one, again, as we've seen in many cases, if your double bond is in a ring, when you add 2 groups syn, they will end up on the same side, so both on wedges or both on dotted lines, not one up and one down. That would be an anti-addition. Now here's an interesting question. Do we need to put plus an antimer here because we've specifically shown the product in its actual stereochemical designation? And the answer is no. Why not? Because it turns out this is a meso compound, that it's not chiral, and therefore if you do this one or you do its mirror image, they would be the same as each other. So you wouldn't say plus an antimer because it doesn't have an enantiomer. It's not a chiral molecule. Its mirror image would be the same as it, so they're not enantiomers. Okay, here are some more examples for you to work on. Just write down these structures and write the structure of the product, and we'll see if they are correct or not. Notice I've written these in several different notations: osmium tetroxide followed 4-bisodium bisulfite in 2 separate arrows or in 1 arrow. And then this is the alternate method I mentioned, where you just put the hydrogen peroxide in directly with the osmium tetroxide as a catalyst, and the reaction happens. So we will answer those questions in class. That's the end of the video. Thank you.